Okay, we're going to look today at the location process and horizontal alignment. So this is the very beginning of what you do when you want to build a new highway, and there will always be an origin and a destination. So the origin destination, when it's a completely new highway, will be the initial point where you tie in with another highway or road or a city or town or village, and the destination will be the same. So when you are looking into this, you will look into feasible routes between this origin destination. So when you're looking at those feasible routes, first you do a desktop analysis, which is called reconnaissance survey. This is a very broad analysis using maps and geographic information representations of reality. And based on this, you will establish where you can have some corridors. The corridor is roughly where the road will be. After that, you will move into what is called a preliminary location survey and then a final location survey. So we're going to talk about those two in a moment. When you are preparing the design of a new highway, if this is on a rural setting, is much easier because you have undeveloped lands and typically you don't have built up areas. You don't have to worry much about interactions with existing roads, except, of course, the ramps and accesses. Typically, when you are dealing with rural highways, you still need to consider the community that is nearby and the projected economic development and the environmental aspects that are related to this. I'm not going to go too deep into those aspects because in your capstone project and pre-capstone project, you might look a little more into this. So I'm just going to skip through and tell you about the reconnaissance survey. So for this, we use air photographs, contours like the ones you did in surveying, and you will also need the location of structures, drainage, utility lines like gas, water, and so on. You need to consider the land use and restrictions. So the type of land uses, if it is just empty land, empty plots, or if you have any residential, industrial, commercial. Also, you need to consider if there's any tunnels, mines, monuments, and heritage sites. I try not to go into too much anecdotes, but an example pops into my head where a heritage site had some bridges that dated from a few centuries ago, and that delayed the process of the highway for a few months. So the ground conditions are also important. So we look into the geological maps, the flooding. The flooding is quite important because you want the elevation of your highway to prevent flooding from getting into the pavement structure. But also, if you are in a mountain area, you might want to pay attention to areas susceptible to landslides, and earthquakes will also affect this because the type of terrain, when there's an earthquake, might trigger landslides. So they go hand by hand. So in this example, you can see from Environment Canada a map that is showing you the geological composition. This is showing you somewhere between Ottawa and La Gaspésie, and also includes a bit of New Brunswick. So here you can see roughly what is the main type of formation of the soils. And this is important for the bearing capacity for the pavement structure. And we will look into this later on in this class in a few weeks. Type of rocks is a little more specific and will tell you if what you are dealing with in terms of the foundation for your highway. Surface material is the greatest degree of information that you will have in terms of the materials that are underneath the road itself. And this is important for bearing capacity, as I said, but also because of drainage. on-site drainage. Another aspect that is important is the land use. As you can see here, is color-coded, in this case, the land use by number of people living per square kilometer. And this will tell you roughly where you have more rural and more urban areas. And that will precondition initially that where you might want to have your road passing by, because you will try to have it in the yellow plots, because this means there's very few people living there and the amount of houses and buildings and structures will be minimized. Productive forest and protected land are two important aspects, because protected land you want to avoid at all cost. Otherwise, you need to step into a mechanism that is called environmental compensation. And that means you will have to buy another piece of land that is like 3, 4, 5 times bigger than what the highway requires, and give that in compensation for the land that the highway is using out of the protected area. So similarly, for a productive forest, you might want to avoid having to pass your road through one of the productive forest areas. Of course, you also have to consider what is underground. And believe it or not, there's multiple lines passing by underground. For example, in this case, you have here in Saskatchewan, in a town called Kindersley, the top is the runway of the airport and some hangars can be seen there. But you have in underground the telecommunications, the fiber optics, the gas for heating purposes, and you also have the potable water pipes running. So if you are looking into something like this, then you need to either relocate the utilities so that the highway doesn't touch them, or have enough coverage so that you have sufficient separation in terms of depth, so that the load of the vehicles don't damage that infrastructure. In this one, for example, you can see the amount of money expected for expropriations. So let's imagine that you already know where the road will pass by. Now you need to acquire the land. In countries like Canada, most of the land in rural areas belongs to the crown, but which is represented by the government. But in other places, more urban, or in other countries, the land needs to be acquired and purchased from the current owners. And part of the expenditure in the construction of your highway is related to the amount of money you need to pay. And the most important component on the delays, on how long it takes before you can start the construction, is the amount of time that you need to do all the legal proceeds and acquire the land for the project. So I'm going to show you a few of the images from a specific location in Saskatchewan. So to illustrate the different type of information you have in your reconnaissance survey. So this will give you the plan area, which is an aerial photograph. So now you know roughly where is constructed, where is not. In this one, which is the same place, you can see the type of land use. So now you know that the UR is urban reserve, so it's not developed. But for example, in the bottom right block, you can see that there is some body of water that is not mapped here on the land use. So this is why it's important to combine the information from different sources. In the next one, if you keep your site in the bottom right, where we have the body of water, we also have now the description. This is a reservoir, and you also can see the contours. These contours will give you first impression of where you have roughly the same elevations. You can see also at the bottom of the image that there's a lagoon, and these lagoons will have environmental setbacks. The setback is a portion, a strip of land around certain items like the lagoon that cannot be touched and needs to be preserved untouched. So a highway, a road cannot pass through those. You can also see the waste disposal site on the left, middle left, and you also have a setback for that one, according to Saskatchewan regulations, 457 meters. So all that is in the white dash area is area that are setbacks, environmental setbacks that you cannot pass by with any future road or highways. In this one over here, you have the transportation network, but if you pay attention to the dash blue lines, you have the different sewage and the collection of water and how it's moving on the ground. For this one, you have the water distribution system. So this is the water mains. And for this one, you have the sanitary sewers. So all this is underground. But look at this. Between the water distribution system and the sanitary system, you see that pipe that is the force main that is right there. So you will need to ensure sufficient coverage if you are passing a road anywhere nearby that. You have the same on the top left portion of the map. Here in this one, you have the storm sewer, and the storm sewer will have some ditches and flooding areas that you already know. That's where you will be discharging the water in case of rain. And also you have the lines depicting the main direction of the runoff. The runoff is when you have rain on the surface, how the water is going to go through the terrains and in what direction it's going to hit. So for the preliminary location, so the one before was just the reconnaissance. Reconnaissance gives you a high-level overview of what you are dealing with. Where are the obstacles? Where is the underground, etc. Now that you have that knowledge, you move into the preliminary location. The preliminary location now is, let's give it a try and try to pinpoint a specific alignment along which the highway will be. And for this, you can still have a buffer of 40, 50, 60, 100, couple hundred meters where most likely the road will be. And you will trace feasible routes. And these feasible routes will avoid all the obstacles and consider all the aspects that might restrict the location. So there is the planimetric map, which will give you the horizontal location of all the features, the topographic map that will give you the contours and the location of features. And on this topographic map is where we will place the horizontal alignment. So here's an example. And you can see color-coded contours showing the different elevations. And in these elevations, you can tell that whatever is in blue is the lower elevations, and this is probably a river. And then whatever is color-coded in red tones is your high elevation, which in this case goes up to 300 meters. You can also see the span. You have about a couple hundred meters between one and the other one. Now we're going to propose the route map, and we will consider those contours, and we will consider also natural and man-made features, and we will place tangents with curves. If you remember from the previous lecture where we look at speed profiles, that's what we had. We had tangents, which are straight segments, and we had curves, horizontal curves. So the same is going to happen now, and we're going to give it a try to maximize the right-of-way and minimize the impact of splitting farmland into two, or splitting some protected area where there might be some animals and stuff. So in this proposed route map, we minimize the destruction of forests, as commented before. We avoid developed areas. If there's a vertical curve, then we need to consider how this mix together with the horizontal curve. And we need to look also what are the most favorable sites for the bridges, for crossing the river. And crossing the river is typically done at perpendicular, at 90-degree angle, and minimizing excavations. So if you look at this one, the yellow line is an initial alignment, an initial horizontal alignment. And what is on the box underneath is the vertical elevations of the yellow line on the top view. And you can see that we are fluctuating from about 120, 115, 110, and then it's dropping towards the 105. But then you can see where you approach the river that it drops even further down. And that's probably the location for a bridge. This is a second alignment. So first alignment, second alignment. In this alignment, this is only the ground. This is only the surface. Okay. And but it will tell you roughly how much you might need to cut and how big are the different movements when the highway is going to be constructed. You are going to have to cut and fill to even it up the vertical alignment you have there with a vertical profile. And this is a final one that you can see. This is probably a no good because you have a lot of gaps and places where you need to fill and even cut in some occasions. So if we look at the three of them, probably this one out of the three of them is the best because it keeps you roughly at about 115, then goes up to probably at about 125, stays there, you feel a bit, and then it drops gently, and then you put a bridge at the end of the alignment where you have the 12.8 miles. So once you have done all this and you did the reconnaissance and then you did the preliminary, now you move into the final location in which you will have to fix where the center line of the road will be. This is the final location and it's not going to move from that place. You might need to gather some additional data on the cross sections. If you remember from surveying, you collected data and constructed cross sections to figure out how the drainage is going to be on the road. And we are going to have to do something like that here. Then you also need to look into the junctions with other roads where you are going to establish what is called control points and also the existing bridges. And of course, you are going to have to trace along the center line some additional lines which will illustrate the edges of the road and the edges of the right-of-way. So a center line for the location of the road, and then two additional lines for the edges of the road and two additional lines for the right-of-way. You will use some leveling data as a next step to build up the vertical alignment. And then after having the vertical alignment, you superimpose the vertical alignment with the terrain. And that superimposition of the two lines will tell you the earthworks that you need to do. Don't worry, guys. I know I'm telling you a lot of information, but this is just for general knowledge because we will have a full class on earthworks. We will have a full class on vertical alignment. We will have a portion of a class talking about drainage. And each of these aspects we're going to also do in the lab, in the tutorial with the software. So for now, it's just a matter of having a general understanding of what is going to happen and how, what are the steps and how we're going to do the actual design. So the levels should be taken in regular intervals. It depends on whether you have curves or not. If you don't have curves, you can go and take every 100 meters. But if you have curves, then you have to take more often the levels and to create the road profile. And so with this, you will have then the cross sections and you will need the different elevations and levels of the cross sections. So the center line and then at different points across the cross section of the road. Once you are dealing with the earthworks, then you have to locate where do you have borrow pits that you can take material from and where you have landfills that you can dispose the vegetable coverage and some of the trees and bushes that you might need to cut or material that you need to discard. You need to also locate where are the different ditches and streams of water, calculate the hydraulic capacity of those streams because the runoff water that the road will collect needs to go into ditches and then eventually into streams like rivers and creeks and so on. But you cannot put into those streams more water than the one that they can handle. And for that reason, you need to also do these hydraulic calculations. And you might need to use your hydrology knowledge to build up the rational method and estimate how much is the amount of runoff. Okay, so this is how this class mixed together with, I think it's CIVI 381, which is hydrology, and there's another one that is for hydraulics. You also need to look into the existing bridges and culverts and what is it that you have right now, and if the amount of water that your road will discharge into the bodies of water will impact the bridges and culverts if the bridge is sufficiently high and if the culvert is sufficiently big in terms of the diameter so that it can handle the future forecast once the road has been developed. So the road location in built-up areas is more complex, is more challenging. It takes many years because of the implications of expropriation and relocation of utilities, and the planning also requires stakeholder management with the local people living there and the different institutions, local government, utility companies, Chamber of Commerce, and so on. So in a built-up area, you need to also consider the traffic volume. In a rural area, you can ignore the traffic volume and the level of service, but in a built-up area, no. If you go back to the first class, when we talk about the highway capacity manual, we look at the level of service for different type of roads. And this one comes very important when you are dealing with built-up areas and when you need to consider the traffic volume and how the traffic volume is going to impact the demand capacity ratio to see if the nearby roads can handle the traffic or not. So I'm just going to step in for a second and try to give you an example, guys. I hope you can see my screen. I'm just going to go here and show you one road that we completed not long ago. And that the ties in are actually presenting that problem that I'm describing. So if you see, this is the ring road that is going around the downtown. But when you come here, and if we go into satellite view, you will see an overspill effect in certain times of the day because the tie-in with the other road is creating trouble. The other road is already coming heavy. So when I say the tie-ins here in the lecture, is that you need to see if the nearby existing roads can absorb the additional traffic that the highway or the road will impose. You also have to have the considerations of cost, user benefits, social impact benefits, and so on when you are creating the capstone or feasibility study for a highway. So on a built-up area, typically you have a very limited number of options. The land uses are all constructed in most of the cases. You need to work heavily on expropriations and annexations. Now let's look a bit on the water crossings. So for a rural or even for an urban one, but this case is for a rural, you can have water crossings in different types, but the most important ones are bridges and some box culverts. This is just an illustration of a cross section of a river. And if you see, you have the water level maximum, which is very low. So the water will never rise to cover your bridge. But in other places, like in the picture on the right-hand side, the water level might go up quickly and eventually and very soon go through above the bridge itself. So for the location of highway bridges, you need to try to plan for the shortest because otherwise you incur in a high cost at a right angle. You need to look at the hydrological characteristics as we commented. And you might need to look a bit on the geotechnicals as well to see if the soil has sufficient bearing capacity for the foundations of the bridge. You have to design those foundations. So here's an example. And you have the bridge, which is aligned at 45 degrees, at 90 degrees with the river approximately. And you can see the maximum level, which is the hash blue on the top. And you can see the maximum level at the bottom as well. These two maximum levels are for the two edges of the bridge itself. And in the middle, you can see the size of the deck area for the bridge itself. Here's another example. This is a more standard US 1960s bridge and the maximum level of water, which is far away from the beams and the superstructure of the bridge. And on the top, you can see that the bridge is aligned at approximately 90 degrees with the contours. Okay, in Canada, we follow the geometric design guide for Canadian roads. We're talking now about the alignment itself. And it contains the highway geometric design guide contains 7 dimensions: mobility, road safety, environmental impacts, aesthetics, capital cost, maintenance cost, and vehicle operating cost. So these 7 aspects you need to consider when you are designing your highway. We talk about road safety already, so we give a full coverage of those aspects. Mobility is nothing else than the amount of time that it takes to travel. Environmental impacts, we have discussed a bit in this lecture. Capital costs a bit. Maintenance, we will not get to talk about this. I will try it towards the end of this course to see if I can spare some time to talk about the maintenance. And vehicle operating costs is something that escapes the scope of this class. But at the end, you have to try to arrive into a compromise where you minimize capital cost, but you maximize mobility, as shown here on the top, okay? So as mobility improves, the amount of money you need to spend is more because you will need more lanes, you will need more gentle curves of radius of curvature, and that's going to make you spend more money in expropriations and so on. As you look at maintenance cost, when you increase maintenance cost, your environmental impacts increase. So there's always a trade-off between these aspects. So the horizontal alignment, you will look into all those aspects as we have discussed and assess the alternatives based on the cost that it takes in the initial construction, the relocation of utilities, but also the cost of maintenance. So you could spend not much money and make very steep cuts in the terrain. But if this is going to make you incur in maintenance and closures of the road because of landslides, then the design is not good. Like in the picture you have here on the right-hand side, where in this mountain road, they have to clean up this landslide. So rather spend more money initially and prevent this from happening than every year having to clean landslides, and close the road for several days a year. For the design speed, of course, you also need to deal with the traffic volumes. We discussed this in the first class. For the road safety, I think you have now a good knowledge on that. And for the environmental impacts, you need to consider if you are splitting habitats in halves, if you are putting into compromise aquifers or streams or forest or heritage resources or so on. So in the horizontal alignment, then we're going to go and throw in a series of tangents, straight lines that will be joined by curves. This is typically traced on top of contours, and that will give you your right of way as well. So here, for example, we have in red the curves of curvature and the radius, 500 meters, 750 for these two sample curves. And these sample curves are aligning a road that is sort of parallel to the rail tracks. It's not going into that hill that is on the left. It is staying at the footsteps and is also avoiding the obstacles, which are those two black boxes on the illustration. For the horizontal alignment, you will have different type of curves: reverse, compound, spiral, and circular. I believe circular curves were seen in CIVI 372 and a little bit on surveying. Let's talk about the others. A reverse curve is composed of two consecutive curves that turn in opposite directions, like the green and pink curves here, that they are used to shift the alignment of a highway laterally. So if you see the blue lines, the top left blue line is your old highway, and the bottom right blue line, straight line, tangent, is your new highway. And because of alignment, or perhaps because of an obstacle or a river, like in this case, you want to shift the alignment from the one of the old into the one of the new highway. And to do that, the best way to do it is with a reverse curve, like the one illustrated here. It is always recommended, of course, to use circular curves of equal radius. So in this case, they are almost there. So you have a radius of 686 on the green one and a radius of 690 on the bottom one. So reverse curves are used if no other solution is possible. In this image that you see, it was used to prevent from going through those houses on the right-hand side. But they produce an effect, a sensation to the driver that is not very comfortable. So compound curves is like one step further, where you will have a series of curves all connected together. And in this case, you're also shifting and changing the direction of an alignment or avoiding some obstacles. So in this case, you want to traverse the river on the red curve, which is the shortest distance to reduce the cost as much as possible. And then you have to go through the green, the red, and the yellow curves to be able to accomplish that. Yeah, I mean, you can see here, this is a satellite image, and you can see the use of compound curves back and back because they're going all the way down into that creek. But these really drop speed, and these really reduce mobility and increase travel time. And of course, there's always some mountain designs that land into something like this. Now, compound curves can be used to enable an exit that was not existent, like in this example. The initial highway was going straight, but now a new exit is required, so you can use a compound curve to go and allow for that. Spiral curves follow the clotoid equation, which is given there. A squared equals RL. R is the radius, L is the length, and A is a constant. And they represent a natural path of transition. They require super elevation always, and we try to avoid them in general and avoid the closed shape spirals overall. So here you can see the super elevation runoff for spirals on a horizontal curve, and you see the design speed on the top. You can see the degree of super elevation, which is the first column, 1.5, 2, 3, 4, 5, 6, all the way up until 12, and design speeds in kilometer per hour. And then whether you have a two-lane or a multi-lane. So the number one is two-lane, the number two is a multi-lane. We are assuming a standard lane width of 3.6. And this is your super elevation for runoff purposes on horizontal curves. So that's the amount that you need to provide. In this one, we have super elevation runoff for spirals. So you have here design speed again and super elevation rates and the tangent length that you require. This one is in feet. Remember the example of the closed shape spiral that I showed you before and the implications on road safety that might have. So for that reason, we try to not use those spirals and instead use circular curves, which people are more used to, designers as well, but motorists, drivers, road users, they perceive this better. And they can anticipate, if you remember in terms of the workload and the perception reaction and anticipation, they are better. Circular curves, they have all these elements that you have seen elsewhere, the radius of curvature, tangent, and the length of curve being the most important ones, the others being only complementary. And of course, the deflection angle, delta, which is also very important because that will tie in the initial point of curvature and the point of tangency. And there's a lot of equations that we can deduct from the horizontal curves. So in this, you can see what is the tangent in relation to the radius of curvature and the deflection angle. You can see in this one what is the value of E, which is there, is just the distance between the point of inflection and the curve itself. The value of M is given by the radius minus the value of the Y, which is there on the figure. So all these you have seen in surveying. I'm just going through again, but you should have seen this in BCE 371 and CIVI 372, if I'm not wrong. The length of the curve, which is the radius of curvature multiplied by the deflection angle, multiplied by pi over 180, pi in radians. We saw this one in the previous class. And of course, if you have an example of a 600-meter radius curvature horizontal curve with a tangent of 120, the PI is in station 5 plus 100, and determining the station of the PC and the PT will take going through the equations that you learned before that will add or subtract from the PI the tangent to determine the PC, but to go from PC to PT will add the length of the curve itself. These are examples that you have done in the past because this is examples just directly taken from the textbook that you use in transportation engineering CIVI 372. But I need you to recall all this because what is going to happen now is that Civil 3D, which is the software we're going to use in the lab, in the tutorial, it will do this automatically for you. But still, you need to remember what's happening behind scenes because you might need to correct the alignments. You might need to increase the radius of curvature. You might need to increase the tangent you might need to play with these elements. The other aspect that you have learned before for a circular curve is the super elevation, which is basically pure physics, as you learned from high school, where you have a friction force and you have the weight of the vehicle acting on the vehicle, and the coefficient of side friction, which is preventing the vehicle from skidding, and a centripetal force that is given by the super elevation, which in this case we call E. And then the radius of curvature is going to be defined by the speed in meter per second divided over the acceleration of gravity multiplied by the coefficient of friction plus the super elevation, because those two are the ones that are holding your car in place without you losing control. And then there's a demonstration here of the same equation that I showed you before. So this is how that equation is being deducted. I'm not really going to ask you to know this. Don't worry about it. You should have learned this before. But the equation at the bottom right, which is the same as the equation here, is the one that we will be using in class. And as a matter of fact, in class, there are tables that will give you the values of radius of curvature recommended based on the super elevation and the speed that you are using in your design. TAC in Canada has this alternate equation. The only difference is that this equation is for metric units, while this equation is for, one of these, depending on the constant, is for metric and the other one is for imperial. So let's look at an example, which is also from the previous textbook. So you have a highway for a speed of 100 kilometers per hour, and the maximum permitted super elevation for any reason is 6%, and the coefficient of friction that we're assuming you will have is 0.12. This coefficient of friction drops when you have black ice, of course, right? And slippery conditions on the road. And this is why you have to drop your speed when that happens. And so it's all about determining the minimum radius of curvature. So if we use the equation from the textbook, your speed will be in meter per second. If we use the TAC equation, your speed will be in kilometer per hour. Both of them will lead to the same answer. Notice you have your 6% super elevation, 0.06, and your 0.10 coefficient of friction. Instead of 0.12, we're being a bit conservative. So we're dropping the value. You could have used 0.12 if you want, and you will have a little more radius of curvature. A little less, sorry, radius of curvature. The TAC and the different design manuals, they will give you tables. This is the reason why you don't have to memorize these equations. Of course, you need to know what is behind the table, how they arrive into this table, because this table is nothing else than using the different assumptions to come up with a design. So from TAC, the maximum friction that you can assume depends on the speed. As you increase the speed, the maximum lateral friction drops. When you are driving at 40 kilometers per hour, your lateral friction can be 0.17, the coefficient. As you go up and you reach to 100, from 0.17, you drop to 0.12. Quickly, as you go from 100 kilometers per hour to 130 kilometers per hour, your maximum lateral friction drops even further to 0.08. So these are the maximum values that you can utilize in your design. That one is for high-speed urban design. For low-speed urban design, you have the table on the right-hand side. Now, this table over here is giving you what is the radius of curvature. So if you remember, we saw those equations, right? which came from this demonstration. At the end, they are embedded into this table where you have the design speed from 40 to 130. You have the super elevation. You start with 0.04, the first portion of the table. The second portion of the table, super elevation, is 0.06. The third portion of the table, super elevation, is 0.08. Then you have your design value for friction. This friction is coming from these tables. And then you add the super elevation and the friction, and that goes into the equation, this one, to give you the minimum radius of curvature. So in the previous class, when we were looking at your radius of curvature here, the R, or if you want in the example, when we were looking at this, the 686, the 690, those radius of curvatures, they are coming from a table that use all those you have learned before and put it all together and come up with the minimum value that you need to use as you calculate. And then that is minimum, of course. You can use more, but this is the bare minimum you should utilize. So, for example, if we are designing and we want to design for 100 kilometers per hour, and we have a super elevation of 0.04, that is 4%, and my friction is 0.12, then my minimum radius of curvature is 492 meters. As the super elevation increase, this in addition to the coefficient of friction, gives you an overall bigger denominator that allows you to drop the radius of curvature. So when you move from 0.04 for 100 into 0.06 for 100 again, you go from 492 radius of curvature to 437. So you reduce about 55 meters, the radius of curvature. If you go into the 0.08 super elevation for 100 kilometers per hour, you would even drop further to 394 minimum radius of curvature, meters. For spirals, there's a similar table where you will choose the design speed. Then you will choose what is the configuration, if it is a 2-lane or multi-lane. And then you will look into what is the radius that will match the spiral parameter, which is calculated with the equation we learned before, which is the length of the curvature divided by the radius, square root. And that will tell you what is that radius, minimum radius that you should look. You should try to avoid these ones, though. Another aspect that is very important when designing the horizontal alignment is the stopping side distance. We already talked a little about this when we're looking at the safety, but I want you to consider two additional aspects. So let's imagine you are the bottom left box, rectangle, that is a car that is coming with the green straight trajectory. And then after the green trajectory that is straight, you start going through the horizontal curve. Now, there is a side obstruction, could be a big warehouse or something like that, that prevents you from looking too far away. And this is gonna compromise your stopping side distance. So the stopping side distance is always between the different points where the eye of the driver will be. And for the eye of the driver, you need to remember that you are using the values we saw in the previous class. So when you are dealing with this stopping side distance, you need to calculate the value of M, which is the offset, until you hit this side obstruction. The value of M is given by the equation that is there on the left. And the stopping side distance is given by the equation that is at the bottom. You can find them on pages 788, 789 of the textbook. So don't worry about the equation. I'm not going to ask you how to demonstrate how you arrive there, but you need to know how to use it. So that stopping side distance is based on the radius of curvature, but the radius is going to the location of the driver itself. Then you have the value of m, which is the offset, and you apply that trigonometric operation to obtain the stopping side distance. ¿Me regalas agua caliente, por favor? ¿Quieres un café porque te estás durmiendo? Necesito algo caliente ahí. So in this chart, you have on the right-hand side the V, which is the speed in miles per hour, not kilometers, miles per hour. And then you have the value of S, which is your stopping side distance. And as you see, you have also the radius of curvature on the left. The vertical left scale is logarithmic, and it's giving you the radius of curvature to the center line of the inside lane. At the bottom, you have the horizontal side offset. This horizontal side offset is the MS that you see over there. So depending on the information you have, you can obtain the horizontal side offset, if you need that, by plugging in the radius of curvature and selecting the speed curve from the graph, and where the two of them hit, you read down and you obtain the horizontal side offset. So, for example, a horizontal curve on a two-lane highway designed with a 2,000 feet radius, 12 feet lanes, and 60 miles per hour speed. And we're going to try to estimate what is the distance that needs to be cleared from the inside edge of the inside lane to provide 570 feet of stopping side distance. So we're trying to estimate the M, that MS value that is there between the trajectory and the obstruction. So we have a 2,000 feet radius. So if you go to the vertical left scale, you are in a logarithmic scale. So you see the 1,000. The following line above is 2,000. So that is where the black line is located at. Then you have 60 miles per hour speed. So if you see the circle over there is pinpointing the location of the speed equals 60 miles per hour. On a 60 mile per hour, we match that with what is the requirement of the stopping side distance, that is 570 meters. So, and that's also there, that's also there on the right-hand side. So for a speed of 60 miles per hour, you have a stopping side distance of 570. So now you go and you hit with that curve the solid black line, and then you throw a red line down, and that will tell you the horizontal sideline offset, HSO. So 20 feet is the value of MS, which is how far that obstruction can be. This one, for example, will be used when you are using dynamite to blow material on the edge of the road as you are creating the right-of-way. So you need to know how far you need to remove the material so that you can ensure sufficient side distance. That's what probably this example could be about. Okay, so this is the material for today's lecture. I'm going to stop the recording.